in Chapter 4. We're rolling right along. Let's see what we can learn about finding derivatives of logarithms. Remember, logarithms are exponents, so let's see where that takes us. Hello and welcome to derivatives of logarithmic functions. We're going to find derivatives, and of course we'll also add finding derivatives using other bases just in case you have a different base. In all likelihood, if you did, it probably would be 10, which would mean it would be a common logarithm, otherwise a natural logarithm, but other ones are possible, so we'll hit a few extra things there. So, just in case you're interested where this comes from, here's our natural logarithmic function. Now, what would you get if you wanted to take the derivative of both sides? Well, the first thing you can do is use each side as an exponent. Take e to the left side, e to the right side. These are inverse operations, so you just end up with x. E to the y equals x. Next, that's easy to differentiate, very easy. The derivative of the left side, e to the y. The derivative of the right side of x. So we'll get e to the y, that's the easy part. Remember, we've got an inside function, so the derivative of that with respect to x is just dy dx. Nothing else to do there. And on the right side, of course, just 1. That's easy. Divide both sides by e to the y, so we can get dy dx, which is what we want. And dy dx equals 1 over e to the y. Now, e to the y is the same thing as x. So dy dx from the logarithmic function, the natural logarithmic function, equals 1 over not e to the y, but its equivalent x. There's the derivative of your logarithmic function, the natural logarithmic function. Just in case you're interested. Sometimes derivations can be rather complicated. This one's fairly easy, and you might have been able to do it, really. So, here are two things for you to remember. Number one, if all you've got is just the natural logarithm of x, your derivative is 1 over x, what we just saw. If you've got an inside function, u, then you still do it sort of like this one, except remember the chain rule. So you have to take the derivative of that inside function, du dx. So what you would do would be you would take u maybe off to the side, take the derivative of that, so you'd have du dx, and whatever you found that was equal to, and you'd be ready. You could put it right in here. Remember, this u is the original inside function without taking the derivative, just the original. So there's the first one. I just put them aside here just in case. Remember, x or any argument, that's what you put into a function, has to be greater than 0. If that argument is a function, then you follow that simple derivative part with du dx, the derivative of the inside function. Now, let's try some examples. So what we've got here is our function, the one we're going to experiment with, is natural logarithm of 2x squared plus 4. And that's your inside function, alias u. So if we want the derivative of that, remember, the derivative of natural logarithm of x is 1 over x. So this will be similar. So just start by 1 over the 2x squared plus 4. But remember the chain rule. We have an inside function, so we have to take the derivative of that. And the derivative of that is just 4x. So our derivative, we have 4x over, by the way, notice, you could divide that by 2, also the denominator, so let's factor out the 2, x squared plus 2. So our derivative for that particular natural logarithmic function is just 2x over x squared plus 2. There you go. Not too bad, is it? You might want to try just pausing or turning this off for a second, or just turning around the other way. Try it yourself. Go back up here to the function itself. Try this yourself. You've just seen it. If you feel very bold, maybe change this to a 3 or some other number. Try it. It should look somewhat similar to this when you get the answer if you've changed it. Next, got the answer for that one right. Part 2. So we've got a new function. Notice we've got multiplication there. That means we use the product rule. So to get the derivative of that, we can take x times the derivative of natural logarithm of x plus the product rule, and reverse the roles. Take the derivative of x and just the natural logarithm of x. Just copy it. So what does that give us? Well, this is x. This one's pretty easy. That's 1 over x plus, and this is easy, 1, and just copy that natural logarithm of x. What do we get? Surprise! 1 plus the natural logarithm of x. I bet you didn't see that one coming. There's our answer for the second one, just like we had. Next one. Our function this time is natural logarithm of x over x. A couple of different ways you can do that. You can use the quotient rule, that would work fine. Or you could do a rewrite in case you'd rather use the product rule. So we could take the natural logarithm of x and x to the minus 1. So our derivative equals, we'll write the first one intact, the natural logarithm of x, and then the derivative of this part, which will just do this temporarily, plus we're using the product rule, so this time we'll have a natural logarithm of x, take the derivative of that, and our x to the minus 1 the way it was originally. Let's see what we've got. Our derivative is, now this is natural logarithm of x, that'll go on the top of a fraction, this goes on the bottom, so we'll have the natural logarithm of x over x plus, now what have we got here? We need to take the derivative of the natural logarithm of x, that's 1 over x, and this is 1 over x. So our derivative of that original function will be the natural logarithm of x over x plus 1 over x squared. Now you want to get a little bit exotic? Alright. If we look at both of those, we've got a common denominator of x squared. So if I take x over x times this one, I'll actually have a common denominator. So our derivative could be written this way. Now you can write it either way, that's fine. I just wanted to show you some extra. So the first one, you would now have x natural logarithm of x on the top, x squared on the bottom, plus that 1 over x squared we already had. So you could write your derivative as x natural logarithm of x plus 1 over x squared. Your choice. Which one do you think looks nicer? Oops. I think I may have a mistake there somewhere. Let's see. Yes. Right back here. See if I can, there we go. Right here. When I had just x down here, it should be a minus x. Minus x, which we can just bring up here. So we'd have minus that, and there's our answer. Okay, clean up. All right, now we want an equation of the tangent line to the graph of f of x equals 2 plus 3x natural logarithm of x at the point 1, 2. So first of all, we want to get the slope. So we'll start with the function, get it all on one line, that helps. 2 plus 3x natural logarithm of x. What's the slope? The general slope is, and you'll get a 0 here. Over here, we'll leave that 3 out front. And let's take this one piece at a time. Take the derivative of x, natural logarithm of x, plus reverse the roles. You have x and the derivative of natural logarithm of x. That should do it. Say 3 out front, good. X one way, x the other way, natural logarithm of x one way. Okay, I think we're in good shape here. F prime of x equals, leave that 3 out front right away. Okay, the derivative of x is 1. That's nice. Natural logarithm of x plus, and then we'll have x, and the derivative of natural logarithm of x is 1 over x. What do we have? Let's see. So far, oops, there we go. Leave the 3 out front one more time. We've got the natural logarithm of x plus 1. Multiply the 3 out. So our derivative is 3 natural logarithm of x plus 3. Check that. I guess we got the steps there. Now, once you got this, oops, let's go back here. Let's go back the whole way. Okay, so we've got the slope. This is the general slope down here. This is the slope of any point, but the one we need is the slope for 1, 2. Maybe we write it this way. Slope of point 1, 2. So we bring this up here. So we need the function, the derivative at a 1, because we put the 1 there, equals f prime of 1. So f prime of 1 equals 3 natural logarithm of 1 plus 3. So our slope is the natural logarithm of 1. Remember, this is talking about what the exponent is. If you take e to some power, you get 1. What's that? What's 0? So this is just 3 times 0 plus 3. So the slope at 1 is a 3. Now we want the equation of the tangent line. So we'll go back to our point slope form. In case you forgot it, y minus, the y value is 2, so we'll put a 2 in there, equals 3 is our slope, and x minus, our x value is 1. There's our equation in rough form. Y minus 2 equals 3x minus 3, and y equals 3x minus 1 when we add 2 to both sides. There's the 3x minus 1. Got it. And there's the graph of the function and the tangent line. Notice if you look back here, there's 3x minus 1. That means it's a little bit on the steep side. It goes through a y-intercept of -1. There you go, just as we found. Notice that over here on the left, on the graph, there's nothing here because natural logarithm function can't take a 0. It has to be a positive number. So it starts off with an empty dot there, and everything else from the right is normal, so to speak. Find our relative extrema on this function. Let's see what we get. I guess we'll find the derivative, right? So I think I've got this one written out already. Let's see. Okay. So you might take a look at the picture. There's a picture of our function, and you can see it looks like it has a minimum around 1. So you write the original function. All we do is copy there. You want the derivative? Remember, this is 1/2 x to the 1/2, so you bring that 2 out front, the 1/2 and the 2 give you 1, x minus, and we're doing derivatives of natural logarithms, and the derivative for that is 1 over x. Next, set the derivative equal to 0 because we want to find the minimum. What's next? You'll make a guess. Add 1 over x to both sides. Then what do you think next? Multiply each side by x, the common denominator. Excuse me. And we've pretty much got it. What squared equals 1? Plus or minus 1. However, excuse me, only with positive ones in the domain. In other words, with natural logarithms, we can only use positive numbers. So we throw out the minus 1. Next, applying the first derivative test, you can check out that it's got a relative minimum at x equals 1. However, what if we have a different base? The gold standard, of course, is E, Euler's number. And what if it's something else? Even if it's a 10, what do? Well, we've got something. We've got a couple of extra formulas, but you can put those on a 3x5 card and have them ready for you. First of all, remember that base has to be a positive number, and 1 would be pretty silly. 1 to any power is 1, so that's the reason why we throw that out. You don't see anything if the base is 1. Next, so here's a logarithm with possibly a different base. This works with any base at all. Now I want to run through this real quickly with you. This, of course, is a logarithm in its general form. The base is in the, I'll call it the basement. It's the lowest number on this, lowest in space. So if you're going to rewrite this, write the base first. It's there staring at you. If there's nothing there, it means it's 10. So keep that in mind. Logarithm base 10 is called a common logarithm. If it isn't showing there, then it's automatically a 10. Now, what do we get for the exponent? Remember I said over and over, logarithms are exponents. That means this is an exponent. So it's a to the b. What do we get? Well, the only thing missing is the x. There you go. Remember, the bases have to be positive numbers. So can you convert those to exponential equations? I'll challenge you. Just take a couple minutes, switch each of those to exponential equations. The practice is, if there are x's in there somewhere, switching it to an exponential equation might make it very easy, and you'll see some of those. Okay, you ready? All right, for this one, start with the base. The base is in the basement, so there's your 2. What's the exponent? Well, logarithms are exponents, so there's the exponent. What's it equal to? Of course, it's equal to 8. It's all right there. Start with the base, pick up the exponent, and this is the result. Base, exponent, result. All the time. Next one, base, 10, exponent 2, result. Of course, you can calculate those in your head, but simple practice is practice. When it gets more interesting, then, but anyway, you get the idea. Third one, base is 10, so you write 10, the exponent's negative 1, 1 over 10. And of course, 1 over 10 to the 1, which is 1 over 10. Last, the base is 3, the exponent's 4, and 81. Now, you can use your fingers on this one. This means you got 4 3's. So 3 multiplied by 3, you got 9. Multiply by 3, you got 27. Multiply again by 3, and you get the 81. I hope that was easy. There are your answers. All right, now, to wrap things up a bit, what if you don't happen to have this particular function in your calculator? Now, as far as I understand, almost everyone in this class has one of these two. TI-84, a lot of you from my view have TI-84 plus, should put a plus there, CEs. And about 2 of you have the TI Inspire. Now they do have something with this look to it. If you know where to find it, you can find this, and you can put in the base that you need to use. You can put the number in here you need, and you can do the calculations. However, if for some reason you didn't have that, there's an easy way to get this, even if you don't know where that is in the calculator. And if you're like me, you forget from time to time. If you don't use it all the time, and I don't, I teach math and I don't use that all the time. However, This is the way that I remember it. You have logarithm base A of some number x. And you think, okay, I'm stuck. What am I going to do? Well, you do have the natural logarithms. So how do you use them? Well, if you look at this expression right here, which one's on the top? The x. Which one's on the bottom? The a. And since we like using natural logarithms the most, natural logarithm, one's on the top, one's on the bottom, the one on the bottom, and the one on the top. It's that easy. The only thing you have to remember is do not accidentally do this. It's not the natural logarithm of x over a, it's the natural logarithm, where's my pen? You have to make a fraction of it. So with your calculator, if you've got the TI-84 plus CE, for example, you can do alpha y equals, enter, and you can get a fraction. Put what you need on the top, put what you need on the bottom, hit enter, you got your answer. If you've got a TI Inspire, you know how to do that. Do a control division sign, you've got the fraction, and then put the things in on the top and the bottom. It's that easy. But you have to remember, if you have to do that, then the x is on the top, the a is on the bottom, all you have to do is take the natural logarithm both and divide the two results. Now what I've done for this one is I've just written them out nice and bold. A couple of things to remember. First of all, now I've rewritten a couple of these. They're exactly the same and even in the same order, but this is the way I remember them. First of all, if I'm doing, where am I? For this one, I know that the derivative of e to the x is just e to the x. Well, this is similar, so if I'm starting this is what I'm going to write down first, but then a reminder to myself, wait, that's not e. I have to make an adjustment, and the adjustment is to take the natural logarithm of the base. That's how I do it. Now this one up here puts the natural logarithm first, and that's up to you. This is my way of doing it. You don't have to do it that way. For the second one over here, this looks similar. So you have a to the u, but remember two things. First of all, you're going to have to take the natural logarithm of a because this isn't e, and because you need to use the chain rule, you'll have du dx. So here, this is like e to the x. This is using the chain rule, and the natural logarithm of a because a isn't e, so you have to make the adjustment. The last ones, not too much different. The difference here is, instead of having the natural logarithm of a on the top, you're going to have 1 over the natural logarithm of a. So when you think of logarithms, the derivative is 1 over that item. The chain rule says, oh, don't forget, you have to take the derivative of u, the inside function, put that next, and then 1 over a because this wasn't an e, it's an a. So you make the adjustment of 1 over natural logarithm of a. Just remember, for the exponents, the natural logarithm of a goes on the top. For logarithms, the natural logarithm of a goes on the bottom. And the last one, if you're going to take the derivative of this, 1 over u, just like 1 over x. Take the derivative because you got the chain rule, excuse me, and because this base is an e, you make the adjustment of 1 over natural logarithm of a. Not natural logarithm of a. When you have these logs, you have to 1 over the natural logarithm of the base for these last two. That won't happen too often. The vast majority of the cases you'll be using e, and you'll be using the natural logarithm of x. An example to take us out. So, many of you, if not all of you, have taken chemistry in high school. And even in physics, you might talk about the half-life of something. That means you got a certain element. In this case, it's carbon. You know that has a chemical symbol is C. Usually that has an atomic number of 12, but for the radioactive one, it's carbon 14. Now you don't have to know that. What you do need to know, and that'll be given to you, will be what the half-life is. The half-life means this. So you've got a box, and inside the box is a lump of this carbon 14. And it's got a certain mass. In this case, it's got a mass of 1 gram. Now, you're going to step into your time machine and go forward 5,715 years. Obviously, you need a time machine for this if you're going to do this experiment. So you start with a radioactive element. You got 1 gram. You jump ahead 5,715 years. What's left? What's left is 1/2 of a gram. That's why we call it the half-life. If you wait this long, half of the original will be left. If we go another 5,715 years, what's going to be left? Well, we had a 1/2 gram, and 1/2 of that 1/2 gram means only 1/4 of a gram will be left. That's how half-life works, in case you didn't know. Here's the formula. In the formula, this is how much you got at whatever time you're interested in. The half represents the half-life. The t represents how many years have gone by until the time at which you're interested. This 5,715 is something associated with the half-life. There are times when you might see this look like this. Instead of the t divided by 5,715, you might see it look like this, and 1 over 5,715 is going to be some number like this. So it'll be 0.00 whatever it is, and then t. Either way works, but you might see it either way. So the question is, at what rate is it changing when t equals 10,000 years? This might not be what you're expecting. You're expecting how much was there. But what we're interested in now, because we're in calculus, is how fast is it decaying 10,000 years from now. So get in your time machine. First of all, start with our formula. We'll go to 1/2. Put in 0.5 if you want. And I'm going to change this 1/5715 t. And you probably know why I'm doing that. Because I'm going to take the derivative because we're talking about what is the rate of change. So dA dt equals. Now what do I get? Okay, first of all, we've got this, and what else do we have? We also have to take the derivative of the inside function, and the derivative of this part right here is 1/5715, but also it's times, because because the base, the 1/2, isn't e, we have to take the natural logarithm of 1/2. And that's going to do it for us. So dA dt equals, and let's see. Well, that's pretty much it. The best we can do would be to take these two numbers, multiply them together, and take the result and move it out front. And then what we're going to do, we're interested in how fast it's changing at 10,000 years. So we'll take the 10,000 and put it in for this t. So this is what we've got in a different order, but it's the same thing. Put the 10,000 in and let that calculator hum. So this says that the isotopes in the object, our carbon-14, are decreasing at the rate of 0.000036 grams per year, or 36 millionths of a gram per year is decaying. End of story. If you have any questions, you know how to get a hold of me. sailorod@wofford.edu. Also sailormath@outlook.com. Until next time, keep smiling. Adios.